Hello students, in our last video we have obtained the expression for starting torque and torque under running conditions. Now we are going to learn the torque slip characteristics of induction motor. Now see, this torque slip characteristics is the family of the curves which are drawn for the various rotor resistances such as R1, R2, R3 and here it is R2 equal to X2. Now this torque slip characteristics can be divided into three basic regions. First one is the operating region, second is the maximum torque region, and third one is the starting torque region. So it is the curves, a family of curves between the torque and slip or torque and slip or in other words torque and speed in speed. Now here it is at slip s equal to 1 the torque developed is starting torque. So when the rotor resistance is R1 the starting torque is Tst. Now when rotor resistance is increased the starting torque also increases. In this way when Tst equal to Tmax here it can be obtained at R2 equal to X2. Now let us see the three regions. The first region here, the when the see let us see the torque equation. Torque equal to K phi SE2 R2 upon R2 square plus SX2 square. Now see at no load condition or light load condition, the slip is very small as the motor speed is close to synchronous speed and therefore the term Sx2 becomes negligible as compared to R2 and therefore torque is directly proportional to S upon R2. Here it is a mistake, S upon R2, and if R2 is constant then torque is directly proportional to slip. Therefore the torque slip characteristics are straight line operating region as shown in the figure. Now see at low slip, the characteristics is directly proportional. That is a straight line as shown. The operating region is shown by the hatch line. When the load increases, the slip increases and the term Sx2 be equal to R2. So this is the condition for maximum torque which exerts the maximum torque as shown in the figure. This maximum torque is also known as stalling torque or pull-out torque or a brake torque. Now the Tmax occurs at different slips as per the rotor resistances as shown in the figure. So this is Tmax 1, Tmax at R1, this is Tmax at R2, this is Tmax at R3 and this is the Tmax at T start. So the maximum value of this torque remains same and that occurs at different values of the rotor resistances or different values of the slips. So here if the load is further increased, the slip also increases and therefore the term Sx2 becomes very high as compared to R2 and therefore torque is proportional to 1 upon S. Thus the curve becomes a rectangular hyperbola after the Tmax as shown in the figure. So when R2 equal to X2 that is the at the time of starting the R2 equal to X2 that is slip equal to 1. Here the slip equal to 1 motor exert maximum torque at the starting as shown in the figure. So in this way we have learned the torque slip characteristics. Now let us develop the relation between the starting torque and maximum torque and full load torque and maximum torque. Let us consider the first the Tst upon Tmax. We know that the starting torque is directly proportional to R2 upon R2 square plus X2 square. Say this is equation 1 and the Tmax is proportional to 1 upon twice X2. Say this is equation 2. Now divide equation 1 by 2. So Tst upon Tmax equal to R2 upon R2 square plus X2 square into twice X2. Now let us divide numerator and denominator by X2 square. So this one of the X2 will cancel and here will be R2 upon X2. So this R2 upon X2 into 2 and this will become R2 upon X2 bracket square plus 1. So let us put A equal to R2 upon X2. So this will be Tst upon Tmax equal to twice A upon 1 plus A square. So this is the relation between starting torque and maximum torque. Now let us develop the relation between the full load torque and maximum torque. We know that the full load torque is directly proportional to SF into R2 upon R2 square plus SF x2 bracket square, where SF is the full load slip. Now divide equation 4 by 4 by 2. Therefore, TFL upon Tmax equal to SF R2 upon R2 square plus SF x2 bracket square into twice x2. Once again divide numerator and denominator by x2 square. You will get the relation TFL upon Tmax equal to twice A SF upon A square plus SF square. So this is the relation between the full load torque to the maximum torque. Now here if we put SF equal to 1 in equation 5, we will get the relation starting torque upon maximum torque. Put the SF equal to 1. So this will be this TFL become TST. So TST upon Tmax equal to twice A upon A square plus 1, because this SF is 1. So now let us obtain the relation between TST upon TFL. So TST TST upon TFL. So already we have obtained TST upon Tmax. So divide this equation twice A upon 1 plus A square multiplied by S square more S A square plus SF square upon twice A SF. This will can be simplified as TST upon TFL equal to A square plus SF square divided by SF into bracket 1 plus A square, where A equal to R2 upon X2 and SF is full load slip. This A is also can be written as a SM, where this is the slip at maximum torque. In this way, we have obtained the torque relations. Now let us see the power stages in induction motor. So how the power flow takes place. So the motor input, that is the motor input to the stator, is a P1. Out of this, if we subtract the stator losses, that is stator CU and iron losses, you will get the rotor input via air gap. Now, the rotor has only the rotor copper losses, because the rotor iron losses are negligible, because the rotor frequency is very small, Fr equal to SF2. That is very small, and therefore the eddy current and hysteresis losses are negligible. So if you subtract the rotor copper losses from the rotor input, you will get the rotor gross output or mechanical power developed in the rotor, that is also denoted by PM, or it is also known as the rotor gross output. Now from this rotor gross output, if we subtract the rotational losses, also known as mechanical losses or the windage and friction losses, we will get the rotor output or motor output at the shaft. So these are the power stages. The same thing, that's power flow tree, this can also be explained by other way. Now let us see the power stages. So motor input to the stator is say P1, and if you subtract from this the stator losses like stator copper loss and iron loss, we will get the rotor input via air gap. From this, if we subtract the rotor copper losses, we will get the rotor gross output or the mechanical power developed in the rotor PM. Now from this, if we subtract the rotational losses or a mechanical losses, we will get the rotor output or a motor output at the shaft. So if we travel from input to output, means from left to right, we have to subtract the losses, and finally we will get the power at the shaft, that is output power. From this we can put the efficiency. The efficiency equal to the output power at the shaft divided by input power at the stator. Now if you travel from say right to left, that is the output power to the input power, we have to go on adding the losses. So see here, the motor output at the shaft plus rotational losses will get the rotor gross output, that is the PM. And in this rotor gross output PM is the mechanical power developed, plus rotor CU losses, we will get the rotor input via air gap. And in this rotor input, if we add the stator losses, we will get the motor input. In this way, we can obtain the various power stages, and based on this, we can obtain the derive various relations, and we will solve some numericals based on these losses. Now let us develop the relationship between rotor CU loss and rotor input and the rotor gross output and the slip. Let us first develop the relation, or let us put the relation rotor gross output equal to rotor input minus rotor CV loss. Say this is equation 1. Now we know the general equation power equal to T omega. So in this way, rotor gross output, that is Pm, equal to Tg into 2 pi n, where n is the rotor speed in RPS. If there were no CU losses in the rotor, then a rotor output equal to rotor input, and a rotor will run at a synchronous speed. Therefore, we can put rotor input power equal to Tg into 2 pi ns, where ns is the synchronous speed in RPS, revolution per second. Now from this, so what is the rotor CU loss? Rotor CU loss is nothing but a rotor input power minus a rotor gross output. That is, subtract equation 3 and 2, 3 minus 2. So we will get rotor CU loss equal to rotor input power minus rotor gross output. So Tg into 2 pi into bracket ns minus n. This is say equation 4. Now let us divide equation 4 by equation 3. The equation 3. So what will be the left hand side? Rotor CU loss upon rotor input power equal to Tg into 2 pi ns minus n divided by Tg into 2 pi divided by ns. So this will cancel. Tg cancel, 2 pi cancel, and this is nothing but the slip. Therefore, rotor CU loss equal to S into rotor input. In this way, we have derived the relation for the rotor CU loss, which is equal to S times the rotor input. This is say expression number 5. Now, from equation 1 and 5, the rotor gross output equal to rotor input minus rotor CU losses. So what is the rotor CU losses? S into rotor input. So we can take the rotor input as a common, and what is the remainder in the bracket? 1 minus S. So rotor gross output equal to rotor input into bracket 1 minus S. Say this is equation 6. Now let us divide equation 5 by 6. Therefore, rotor CU loss upon rotor gross output equal to rotor CU loss equal to S into rotor input, and rotor gross output equal to 1 upon S into rotor input. Rotor input will cancel, and remainder is this one. So rotor CU loss upon rotor gross output equal to S upon 1 minus S. Now how to remember this? See, we know the rotor CU loss is directly proportional to S into rotor input. So it should be at the numerator, it should be S, and rotor gross output equal to 1 minus S into rotor input. So it should be 1 minus S at the denominator. If you reverse this, obviously it will be this. So from this we will obtain the another relation, that is the rotor efficiency. So the rotor gross output Pm upon rotor input, that is a rotor efficiency equal to, so this rotor gross output is nothing but 1 minus S into rotor input. Let's take this rotor input on this side. So this is 1 minus S, and that is nothing but N upon Ns equal to efficiency of the rotor. So this 1, and what is S? S is nothing but Ns minus N upon Ns. So after simplifying, this Ns will get cancelled, and therefore rotor efficiency equal to N upon Ns. So rotor efficiency equal to N upon Ns equal to 1 minus S. Now finally, the motor efficiency equal to motor output at the shaft divided by motor input at the stator. Now here the rotor CU loss depends on the are nothing but the hysteresis losses and eddy current losses, which are the frequency dependent losses, and they are negligible because the rotor frequency Fr equal to Sf, which is very small as compared to the stator or supply frequency, and therefore the rotor iron losses are negligible. So in this way we will finish this video here, and some numericals are left for the listeners for solving. So in this way, in this video, we have learned the family of torque slip characteristics, that is in three regions. First region is when at light load, that is the relation is linear. When R2 equal to Sx2, the torque becomes maximum, and later on when the load is further increased, the slip increases, and therefore the term Sx2 becomes greater than the R2, and therefore the torque is inversely proportional to slip, and it becomes a rectangular hyperbola. And finally at slip slip s equal to 1, that is at standstill, we will get the starting torque. Okay,